All right, folks, this will be a quick. Okay, here is a quick video on optimization. Please, as you watch it, maybe take a moment to work through the problem with me, and then we'll pick back up with this material on Monday. So let's say we have a situation where we have, we're going to build a rectangular fence. One side is going to be against a wall, so there's no fence on that side. The material we have measures 400 feet. Then we want to know what dimensions the fence should be to enclose the largest area. So our goal here is to set up a dimension X, a dimension Y, dimension X, dimension Y, dimension Y, dimension X, so that we get the biggest area in here. So we've drawn a picture. That's usually our first step. Then let's come up with some equations that express our situation. And what we're really going to want is an equation for area, since that's what we want to figure out, to maximize. We want an area equation. We're going to call that equation an objective equation. So our objective equation, the equation we want to optimize, in this case maximize, is area, and area is equal to X times Y in our picture. Then we just said this is the equation to optimize. And by optimize, we mean to, we want to work with that equation and make it the biggest value we can find or the smallest value we can find. Now, what else can we come up with? We've come up with one equation here for our objective equation. We could also come up with what's called a constraint equation, which is just another equation related to the situation. And for example, we could come up with a perimeter equation. That would be X plus 2Y. That would be this side length there plus the other side lengths, and we know that that's going to be 400 because that's the material we have to work with. So, and we also could tell that X is 400 minus 2Y, and doing that, so with our objective equation, we're going to want to put our objective equation into one variable. So now express our objective equation in one variable. In one variable, and it could be in terms of X or Y. Let's make it in terms of X. So let's write area in terms of X. We know area is X times Y, and we actually, you know what, I solved for X. So let's go back. Let's change it to area of Y would be X times Y, and X is 400 minus 2Y. That's what we have from over here, and then times Y. So we end up with area in terms of Y is 400Y minus 2Y squared. This is the objective equation that we're going to work with to maximize the area of the enclosed region. Next step, now that we have our objective equation, let's find a workable domain for the objective equation. Again, we have A of Y is 400Y minus Y squared. Let's see, what could our domain be? Domain of A of Y. Well, A of Y is a polynomial, so it's negative infinity to infinity, but that doesn't make a lot of sense because we only have that same Y could be all the way to infinity, but we don't have that much material. We only have 400, what was it, 400 feet worth of material. So why we couldn't put all 400 to just one of the side lengths, for example. So we, let's go back down here, let's say, but Y has to be positive because it's a side length, because it's a side length. And what else do we need to know? So I think y would be, so let's look at our problem. So we decided, I guess you could come up with this a couple ways. Let's say we decided to give all of our fence material to y, then we would have 200 feet here, we'd have 200 feet over there. So the most y could be would be 200. So y has to be less than or equal to 200. X also needs to be positive because it's a side length. And we know that x was equal to 400 minus 2y. So if x is equal to 400 minus 2y, and this has to be bigger than 0, then we could solve for y. We could add the 2y to both sides, divide by 2, and y has to be, and let's say, yeah, I guess we could change that. X has to be, y has to be bigger than or equal to 0. It doesn't make sense, I guess, realistically, for in our picture, for y to be 0. If y is 0, then x gets all 400 feet. If x is 0, then y gets all 400, which means each side would be 200. Either way, you don't get a rectangle in that case. Let's give us some more room. So, for example, the rectangle, when y is equal to 200, here's our wall. We would have two side lengths like this. We'd have y and y, both equal to 200. We would have no x. X is equal to 0, and we get no rectangle. When x is equal to 400, then again, here's our wall. We would have some distance here. That's 400. That's x. And then there's nothing here. Y is 0 and no distance there. Y would be 0. Again, in either case, no rectangle. No rectangle. In either case. But what does that tell us? That tells us that y, for the domain of our objective function, y has to be less than or equal to 0. So our domain for a of y is y has to be less than or equal to 200 and bigger than or equal to 0. So now let's take our equation. A of y is 400 y minus 2y squared, and let's optimize it. So we know that, again, we're looking for a maximum value that y takes so that the no, we're looking for a maximum value for a of y, and that's going to either happen when y is a critical point or when y is an endpoint, 0 or 200. We already know that 0 and 200 do not give the biggest rectangle. When y was 0, we did not have a rectangle. That is our automated cat feeder with Annie's voice recorded telling the cats to come eat. When y is 200, we don't get a rectangle. So let's find a critical point, and that is going to be the location of our max value. our max area. So if we find a critical point, we need a prime y, that's 400 minus 4y. This exists. The derivative exists on 0 to 200, so no critical points of the area function this way. The other way is to set the derivative to 0. So 0 is 400 minus 4y divided by 4. And y is equal to 100. Here's a critical point then. Critical point of a of y. So again, our function's continuous on the closed interval. Extreme value theorem says the max value will happen at 0, 200, or 100. It did not happen at 0, did not happen at 200. It's going to happen at 100. And we can justify that with our first derivative test or our second derivative test. So if we did our first derivative test and we drew a number line and put down 0, put down 200 and put down 100 in the middle and picked a test value of, say, 1 in that interval, picked a test value of 101 in this interval, and we're going to test those into the first derivative. So those are y values. Then we've been writing a prime of y and a of y. So for a prime y, we had 100 minus y for our derivative, or our simplified derivative, 100 minus y, and we want to test a prime of 1. A prime of 1 is going to be 99, and that's positive. Positive on this interval, a of y increases. A prime of 101 is negative 1, that's less than 0. Derivative's negative. Graph decreases. That tells us that a of 100 is our max value. In other words, the rectangle of max area happens when y is equal to 100. Then that's the first derivative test. We could also use the second derivative test. We use the second derivative test. We need to take that critical point of the function, plug it into the second derivative. Our second derivative, a prime y, is either negative 4, you could write it, or negative 1. Let's write it as negative 4. And that's negative all the time for all x in 0 to 200. So that means a of y is concave down, and it's concave down at a of the critical point. So a of 100 is the absolute max in this case. That is a quick, I don't know, this is a case for why the second derivative test is maybe useful, because you can decide really quickly that it's a concave down situation, giving us an absolute max at a of 100 without having to do all the test values, because your second derivative is so quick and easy and negative all the time. Then the last thing to do is answer the question. Question is, what was our question? Our question was, what are the dimensions of the fence that enclose the largest area? So the dimensions of the fence that enclose the largest area, the dimensions that enclose the largest area are y is equal to 100 feet, and x, what would x be at that point? X would be, so if we we could do that two ways. We could come back here to our x equation. X equals 400 minus 2y, put in 100. So 400 minus 200, x is going to be 200. You could also just come back here and say y would be 100. That means this is 100. That means 200 is left out of our 400. So x is going to be 200. Back down here, and x equals 200 feet. Notice it did not ask us for the max area. It was just asking us for the dimensions, which we listed. If you wanted the max area, you would need to calculate a of 100 and compute that. Okay, that is enough. We will pick this up on Monday, and I will post these notes in our OneDrive. Okay, y'all take care. Have a good weekend, and see you on Monday.